So my name is Nicolas. I'm a first-year PhD student at INRIA. I work as part of my work is part of the ERC project on geometric statistics with Xavier Pennec. And I'm going to talk about how to implement symmetric algorithmic components for shape analysis with diffeomorphisms. So the main motivation for this work is to perform population studies, statistics, of temporal deformations. So here we have two cardiac sequences for two different patients, represented by 3D meshes. And as you can see, each myocardial deformation is specific to the anatomy of each subject. So we cannot have a general clinical criteria on the deformation itself to assess disease progression or therapies, etc. So we need, in some sense, to normalize the deformations and to find the equivalent deformation of a common anatomy, of an atlas. And in this framework, we will use parallel transport. So we focus on the deformation between the two extremal points of the deformation, between end diastole when the heart is relaxed and end systole when the heart is the most contracted. And so we focus on this deformation and assume that we can represent the deformations by geodesics in a space of diffeomorphisms that I will explain. This allows us to represent the deformations as tangent vectors on shapes. And then we can transport these vectors in order to complete this parallelogram and to compute an equivalent atlas at end systole. So, and in order to perform parallel transport, we use an approximation that was proposed by Marco Lorenzi and Xavier Pennec, which consists in building geodesic parallelograms. So if we want to, if we compute the deformation between S and S prime and we want to transport it to T, we need to find the geodesic between S and T to find the midpoint between S and T. So we should halfway on this geodesic. Find the geodesic between S prime and M, continue it, find the geodesic between T and T second, and invert it. And this builds an approximation of parallel transport. So here T prime is the equivalent of S prime, but as deformation of T. And this is an approximation of the parallel transport of the vector U along the geodesic with initial speed v. And the error that we make using this approximation, we have a Taylor expansion of this error. As you can see, it's exact at order 3, and the error is of order 4. And the only terms that we find in this error are due to the covariant derivative of the curvature. And this motivates the use of symmetric spaces because, as you may know, they are characterized by a zero covariant derivative of curvature. And by symmetric spaces, I refer to a manifold that is endowed with a family of mappings that are called symmetries, that are defined, that are indexed by each point of the manifold. And they have 4 properties. So they're smooth, and smooth with respect to M. They have only one isolated fixed point. They are involutive. So if you apply twice the symmetry, you come back to the same point. And the property that we call transvectivity means that the parallelograms here commute. So if you first compute the symmetry with respect to S, then with respect to M, or first with respect to M and then with respect to T, you obtain the same result. And in a symmetric space, in fact, there's a canonical affine connection that is compatible with the symmetries, and it's unique. And by compatible, I mean that the symmetries correspond to reverting the geodesics. And with this affine connection, this canonical affine connection, the curvature is constant everywhere. And as a consequence, the pole ladder scheme is exact, and not just at the fourth order, but it's exact at all orders. And so, so by fixing the symmetries in a space, we actually fix the differential geometry structure of the space, and so it defines the connections, the geodesics, the parallel transport, and the curvature. And it may not be a metric Riemannian space. The connection may not be metric, or it may be, but in practice we will focus on abstract symmetric spaces without metrics. In order to compute parallel transport, there has been other implementations, such as the spanning scheme, which was first proposed by Laurent Younes and implemented by Maxime Louis and presented here 2 years ago. It's based on Jacobi fields, so it's a first-order approximation that requires only to compute exponentials, the geodesics, whereas in the pole ladder that we use, we need to compute both exponentials and logarithms. And logarithms are harder to compute because there's an optimization problem. But it's a third-order approximation. And in fact, the trade-off between the numerical stability of the logarithm and the gain that we have because it's a third-order method is not yet very understood. And the computational complexity and the stability of the method is yet to be well studied. But it's exact in symmetric spaces, and that's why we focus on this method. So the key ideas in this work is that we need to validate the parallel transport method beyond its implementation. And we use symmetry because it's often useful to reduce numerical errors. And so the key components here in this algorithm are the symmetries themselves as maps. And so we will also decompose the space of deformation of shapes with a part that is due to the deformation of a template and a part that is due to the residual. And we will see how it improves the consistency of our parallel transport scheme. And it helps us to assess the symmetric properties of the registration framework called LDDMM. So LDDMM is large deformations diffeomorphic metric mapping framework to perform shape matching or shape registration. It works by considering a family of diffeomorphisms that are parametrized, that are defined as flows from the identity, and so flows of vector fields, and the parametrization of the vector fields is decoupled from the deformation itself by introducing control points in space and momenta that are dual to the vectors, to the vector fields. And the vectors are then obtained by a convolution with a Gaussian kernel of the control points and the momenta. And this, in fact, embeds the space of vector fields that we use in a reproducing kernel Hilbert space with the following kernel product. And this Hilbert space is we identified to the tangent space at the identity of the space of diffeomorphisms that we consider. So this is how we get the tangential representation of the deformations through the vector fields. And the goal is to perform statistics on these vector fields because they live in a Hilbert space, so a linear space. But this scalar product on the vector fields also allows us to define a metric on the diffeomorphisms and on the shapes that we study by defining it by right invariance, by computing the energy along the curve of the vector field that parameterizes the diffeomorphism. And with that energy, the flow is geodesic if and only if the control points and the momenta follow the Hamiltonian system here, which means that if we have initial control points and momenta, we can integrate this system in order to compute the control points and momenta at each step of the geodesic. And so we can actually perform geodesic shooting. So we can compute the exponential by integrating these equations. And this is what we use to perform shape registration. So the optimization criterion is here. It's optimized over C and mu, which parameterize the deformation by a gradient descent. And the first term is the data attachment term, and the second term is the regularization for the speed of for the energy of the diffeomorphism. And we will use the implementation of LDDMM in the Python package Diffeomorphica, which was implemented at ICM by another INRIA team. So here with this framework, we define a metric on the diffeomorphisms that then defines the distance on the shapes. So it defines the whole differential geometry structure on the shapes with a connection, geodesics, parallel transport, and curvature. And this is the structure that we try to approximate with our symmetric structure. So in order to be more symmetric and to perform more precise computations, we will use the registration error. So here it's delta, which I often refer to as the residual. So, and it's a displacement field between the corresponding points of the meshes. And so this decomposes the space of shapes with a part that is due to the deformation of a template and a part that is due to a residual displacement field. And the key parameter here is the regularization parameter alpha that makes a trade-off between the residual part and the deformation part. And the extremal behavior are when alpha goes to 0, we're performing exact matching. We're forcing the shapes to match, and we're in the LDDMM framework with the differential geometry structure. But as alpha grows, the deformation part reduces and the residuals increase until when alpha goes to infinity, there are no deformations and only displacements. And so this is a framework of point distribution models, PDM, that are very commonly used in shape analysis. So by varying alpha, we have a continuous interpolation between these two schemes. And consistently with this decomposition, and in order to perform parallel transport, we compute a midpoint, M, between two shapes T and S, by shooting halfway on the geodesic between the two and applying half the residual. So the implementation with LDDMM is quite simple. We just need to perform one registration of T on S, compute the residual, shoot halfway, and apply half the residual. However, in practice, it's not symmetric in T and S, because if we start by registering S on T, we'll get a different, because LDDMM is not symmetric, we get a different diffeomorphism, so a different midpoint. And this is a problem because we would like to define a midpoint in a non-ambiguous way. However, we will see that using the residuals, we reduce this midpoint error. And the key point of this work is that we also define a symmetry with this framework. So the implementation is the same. We register T on S, compute the residual, revert the geodesic, so by shooting in the opposite direction, and applies the inverse residual. So this implements a symmetry on the shape. And now we wish to test whether these symmetries actually verify the axioms of a symmetric space, of the symmetries in a symmetric space. So we will test on real data, on real cardiac shapes. We will test 4 properties. So the midpoint property, the midpoint definition, which I've mentioned. The centrality, which tests whether M is actually the midpoint between T and the symmetric of T respect to M, which is what we would expect in practice. And we test the involutivity, so we perform 2 symmetries and see how far we get from the initial shape. And finally, we test the transactivity, so we go in the 2 directions in the parallelograms and compute the error between the final shapes. And this error, in theory, is quite close to the parallel transport error, because parallel transport is equivalent to a transaction. So as you can see, the error that we make is also a fourth order approximation that depends on the curvature, on the gradient of the curvature. And here are the results. So in blue, this is the the symmetry with the residual. In orange, without using the residuals. And in green, this is a similar error that stems from the registration, so that we can compare to. So as you can see, and this is alpha, the regularization parameter is varying here on the x-axis. So as you can see, by using the residuals, we perform much better than without using them. And we, in fact, compare well and outperforms the inverse consistency of the registration. So we really have a midpoint that is defined in a precise manner, as precise as the registration itself, which is quite good. And we observe the same behavior for the centrality and for the involutivity. So using the residuals, we have a symmetry that performs quite well on the shape. However, the behavior is different for the transactivity because, as I mentioned, it depends on the symmetric properties of the space. So as you can see, when alpha is small, goes to 0, the transactivity error in fact increases, and this is because we are in the LDDMM setting that is not symmetric in practice. And as alpha grows, we go back to the PDM framework that is Euclidean geometry, which is of course symmetric. And so using residuals, the error goes to 0. And it also goes to 0 when we don't use the residuals, but when alpha goes to infinity, there are no deformations. So in fact, everything here goes to 0. And there's an optimal alpha for which the space is closest to being symmetric. And finally, in order to assess the quality of the parallel transport itself, we measure the area strain of the deformation. So on the original patient's data, we have a deformation between n diastole and n systole. We compute the relative variation of areas of each triangle of the mesh. And we expect this quantity to be conserved by the parallel transport when we map it to the atlas. And so we measure the same quantity, but between the atlas and the equivalent n systole atlas that we obtain by the parallel transport scheme, and we compare the two. And as you can see, again, using residuals, we have, and consistently with different regularization parameters, we have a lower error than not using residuals. And in green, this is the fanning scheme, the first order implementation based on the Jacobi fields. And finally, to give you a feeling of the map that we get, so this is the area strain. This one is the area strain map on the subject, computed between these two deformations. And then we transport it with our usual parallelogram and compute it between the obtained atlas and the original atlas at n systole. And we do this with the three methods: the fanning scheme, the pole ladder without the residuals, and pole ladder using the residuals. And so the goal is that this map corresponds to the original one. And as you can see, the main artifact is near the valve, the pulmonary valve, and but it's lower when we use the residuals. And in general, the values are a bit smoother and lower using pole ladder than using the fanning scheme, and then from the original deformation. And finally, to show you the results of the parallel transport. So this is the same parallelogram, and these are the shapes that we obtain with the three different methods. So as you can see, they're quite similar, but we find this bending effect on the valves with the fanning scheme and with for ladder without the residuals, but not using the residuals. And as you can see, this gives we obtain admissible shapes using this scheme. So to conclude, we introduced residuals to compute the midpoint and symmetries between shapes. We use the symmetries as a basic algorithmic component, and this improved, using the residuals, improves the centrality and the other properties of the symmetries. But the transectivity can be interpreted as the curvature gradient of the space that we study. And using the residuals, we have a continuum of decompositions between LDMM and the Euclidean space. And in the future, we will, of course, perform the statistics on the tangent vectors on the atlas, but also try a different registration framework based on stationary velocity fields, which are, in theory, more symmetric. And we could apply the same decomposition on images rather than on mesh, because the residuals could be interpreted as intensity variations, intensity bias, which are hindering the registration results in practice. So thank you for your attention, and if you have any questions.
Since this is a session on computer packages, is there a package available?
Yes, so the package that I use is Diffeomorphisms. It's available in Python, in C++, maybe MATLAB. And it works quite well on meshes with LDMM. The symmetries are not in there yet.
So will you contribute then?
Yeah, maybe it's a project.
I think there is a first version of what you did or what Shuman did that we implemented in Jamstat. There is one small bug of code for parallel transport. I don't think it's that one, but it's the former version. Yeah.
In implementation, you have control points, right? Did you look at what is the effect if you start having more or less control points in the parameterization of the information?
I didn't try because I tried indirectly. The number of control points is fixed by the size of the kernel. So it's they're spaced by the sigma of the kernel initially, and so by varying the size of the kernel, you put more control points at the beginning, and you obtain more precise results. But in practice, here I only used 60 control points for about 1,000 landmarks on the mesh, and this performs very good registration, so we don't need that complexity.
Just another question related to that. Do you think of using that to estimate the curvature actually of the manifold of landmarks? Because since your formula involves the curvature.
Yes, so that's why we interpret the transectivity error as a proxy to measure the curvature. But we could think of schemes to do this more precisely, but I haven't done it yet.
You could compare to there is a formula to compute actually the curvature.
Yes, but it's very complicated, yes.
But it has been implemented.
You said that there is one alpha or displacement value for which you attain maximum symmetry in your space, yes? Mm-hmm. Can you also say if this symmetry corresponds to a nice result compared, in your...
Yeah, so in practice, this is the alpha that I chose for the result that I showed later.
Okay, so it's satisfactory for your application?
Yes, but it's satisfactory, but in fact, the area strain, for example, that we measure, it's quite consistent with alpha. Using the residuals, we get the results are quite consistent with alpha, so it's not as sensitive. But the sensitivity is the definition of the symmetries.
no more questions, then let's thank the speaker.